up until now, I've pretty much just alluded to the events that occur during a complete cycle of the heart with its contractions, relaxations, etc. And I really haven't talked about the manners in which the blood flow, which directions the blood flows, and how the ventricles and atria interact with each other. Well, I'm going to do that now. And the topic that we're covering here is called the cardiac cycle, and this is the complete sequence of events that happens in one complete contraction and relaxation of these cells in the heart. Before I do that, though, let me first just make sure that we're all on the same page with respect to some terms. I mentioned previously that systole is a term that is synonymous with or the same as contraction, that diastole is synonymous with or the same as relaxation, that normal sinus rhythm is that roughly 100 beats per minute rhythm that the sinus, the SA node would have if we didn't have the influence of the parasympathetic and sympathetic nervous system. With the influence of the parasympathetic and sympathetic nervous systems, the normal rhythm for an adult is somewhere around 70 to 80 beats per minute. So in other words, the parasympathetic nervous system is contributing to a slight slowdown of contraction. Tachycardia is any time my resting, and that's the critical thing there, my resting heart rate is greater than 100 beats per minute. So if at rest a person's heart is beating more than 100 times per minute, they have a condition called tachycardia. At the opposite end of the scale from that, if a person has a resting, again, heart rate that's less than 60 beats per minute, that's considered bradycardia. Bradycardia can happen in really top fitness athletes because our heart is so efficient it doesn't have to beat as many times per minute. It can also happen with a number of diseases. The last thing I want to talk about on this in terms of terms on this slide before we get to actually looking at the cardiac cycle is the term palpitation. Palpitation is anytime you have a conscious perception of a heartbeat. Usually when people say, oh, I felt my heart skip a beat, what they're feeling is a palpitation. And because they're consciously aware of it, we call it a palpitation. So let's look at the cardiac cycle. And again, this is the sequence of events that happens in the heart throughout the time period when we have depolarization and then contraction and repolarization. All of those events together form the cardiac cycle. Traditionally, the cardiac cycle is considered to begin with what's called the relaxation phase, or what's called the quiescent period. And that, if I were to highlight it on this ECG down here, is this flat region here between the T segment, or the T wave, and the next P wave. That's when the ventricles are in diastole, the atria are in diastole, repolarization has occurred, everybody's back at resting membrane potential, the muscle cells are relaxed, nothing's going on. This is relaxation phase. So all chambers are in diastole. And the ventricular pressure is lower than the atrial pressure. The reason for that is when the ventricles relax, the atria had already been relaxed before them and blood had been flowing back into the atria. And as a result, the pressure of the blood continuing to flow into these atria has contributed to a greater pressure in the atria relative to the more or less empty ventricles. There's actually a little tiny bit of blood in the ventricles, but it's pretty small. So we have greater pressure in the atria, lower pressure in the ventricles. That's important because that means we have a pressure gradient. Remember, a gradient occurs anytime you have a difference between two locations. That difference could be difference in pressure, that difference could be difference in voltage, it could be difference in chemical concentration. That gradient, that pressure gradient, means that we're going to have a passive process of blood flowing from where it's in greater concentration to where it's in lesser concentration. So we just get this passive movement of blood from the atria into the ventricles. That process is called ventricular filling. obviously, we're filling the ventricles. And again, it happens because the pressure in the atria is greater than the pressure in the ventricles. And when the pressure is greater in the atria than it is in the ventricles, those AV valves will open up and blood will just passively flow. Key point here, passively flow from the atria into the ventricles. The vast majority of ventricular filling is passive in nature. Most of the blood that enters into the ventricles does so passively because of that pressure gradient. That's important to keep in mind. Only probably the last, roughly 20% or so of blood that enters into the ventricles enters there because of active filling. The active filling occurs because of the contraction of the atria. When the atria contract, they squeeze that last little bit of blood into the ventricles so that the ventricles are optimally filled before they themselves contract. So that's the active part of ventricular filling. Now, your book attributes about 30% of ventricular filling due to atrial systole or atrial contraction. I've seen numbers closer to 20% elsewhere. I'm not going to ask you on a test what percentage occurs because of atrial systole, but what I want you to be very clear about is that the vast majority of ventricular filling is passive and only a little bit of it is this actual active process. Now, by the time we get done with the active contraction of the atria, the active filling part, the ventricles are maximally filled. I've put as much blood in those ventricles as I can squeeze. At that point, I have a value called end diastolic volume. End diastolic volume is basically another way of saying the maximum amount of blood that you'll ever get in the ventricles. And it happens at the end of diastole. And we're talking about the end of the diastole of the ventricles. When the ventricles are all done relaxing and we've maximally put as much blood in there as possible, we have end diastolic volume, or EDV for short. Now what? Well, now the ventricles have received the maximum amount of blood they're going to get. Now they need to contract. So we've moved from the P wave and the P to Q line. Now we're into the QRS part. This is where we get, remember, depolarization of the ventricles so that we can then, during the S to T line, have them contract. So during ventricular contraction, this process involves obviously that pacemaker potential going from the SA node to the AV node, down the bundle to the bundle branches, up the Purkinje fibers, and then spreading out across the entire myocardium. And this causes contraction to begin to occur in the ventricles. Now, when the ventricles first begin to contract, they aren't moving blood anywhere. They're just shortening, but blood is not moving back into the atria, and the blood has not yet entered into places like the pulmonary trunk or the aorta. So it's all still in that chamber. So we have this portion where there's no change in the volume yet of the ventricular blood is called isovolumetric contraction. The contraction is occurring, but the volume is staying the same. Iso means same, like an isosceles triangle has two sides that are the same length. So isovolumetric contraction means same volume contraction. And this contraction eventually reaches the point where the pressure inside the ventricles, here and here, the pressure inside those ventricles is sufficient to overcome the pressure in the aorta and in the pulmonary trunk. Okay, the aorta and the pulmonary trunk are full of blood, and that blood is pushing down on those semilunar valves. And until the pressure in the ventricles is greater than the pressure in the aorta and the pulmonary trunk, those valves won't open. But once the pressure in the ventricles is higher than the pressure in the aorta and the pulmonary trunk, then those semilunar valves open, and we get our next phase of the cardiac cycle, which is ejection, or ventricular ejection. This is where we actually get the pushing of the blood out into the aorta and out into the pulmonary trunk. Okay, that's ventricular ejection. Now, at the end of ventricular ejection, there's always going to be a little residual blood left in the ventricles. The ventricles do not or cannot squeeze all the blood out. There's always a little bit of blood left over. That little bit of blood that remains after we're done contracting the ventricles is called end systolic volume, or ESV. So we had end diastolic volume, now we have end systolic volume. Now during ejection, roughly about 70 milliliters of blood gets ejected out. When we're all done contracting, the residual amount left in there is somewhere around 60 milliliters of blood that's always still left in the ventricle. After we've had isovolumetric contraction and then we've had ejection, the next thing that has to happen is the ventricle needs to relax. This is called isovolumetric relaxation. And the reason it's called isovolumetric relaxation is that all of the chambers are still closed. The semilunar valve has closed back down again. The AV valves are still closed, so there's no new blood entering into the ventricles. So the volume is remaining the same again. We're just at end systolic volume, but the ventricle is relaxing. This is again what's happening, remember, in the T to P segment here. This is the relaxation of the heart, and this is going back into the next quiescent phase, or what do we call it, the relaxation period. Okay. Now at some point here, we're going to start to get such an accumulation of blood in the two atria that the pressure in the atria becomes greater than the pressure in the ventricles. That will force those AV valves to open back up, and blood will begin to passively move from the atria into the ventricles again, and we start the whole process all over again. So to sum all that up, here is a figure from your book that shows sort of a cross-section of all the things that are happening in the heart, and how that relates to the sounds we hear if we're listening with a stethoscope, how it looks on an ECG. Up here is a diagram showing you how pressures change in the ventricle, left ventricle, and left atrium, and in the aorta during all of these processes of diastole, systole, etc. And we'll probably spend some more time on this in class and look at how all of these points and figures relate to one another. Let me just take one here as an example. Let's focus on this red line here. Excuse me. This is the indication. Let's do the black line instead. That'll be better. This black line here represents the ventricular pressure throughout a cardiac cycle. And we're going to start with diastole, the relaxation phase of the ventricle. So during the relaxation of the ventricle, you can see this black line is flat. That means the pressure in there is very low. Really, the only pressure associated in the ventricle is related to the end systolic pressure associated with the end systolic volume of blood. So that pressure is pretty low, but notice it begins to climb as we have the aorta, the atria contract and squeeze in a last little bit of blood into the ventricles. We get a little increase in the pressure in the ventricles. And then the AV valve closes. Now the ventricles are going to start to contract. And as they do, look at the huge change in pressure that occurs here. We get a very large increase in the pressure in the ventricles as the ventricles contract and squeeze that blood. And notice then that when the AV valve opens right here, that pressure is dropped way down as the AV valve opens, because now we're ejecting the blood into the aorta or into the pulmonary trunk. The pressure drops back down. And as the ventricle relaxes again, we go into a much lower pressure value. Remember again that the atria are doing something different. Their points of pressure, height, or great pressure, and their low pressure points are different from the ventricles because the atria contract at a slightly different time and relax at a slightly different time.